Okay, let's get back to more fraction division. This time, I want to talk about how to find kind of a shortcut using multiplication so that we don't have to draw a model every single time we're faced with fraction division. Okay? But I'm not just going to show you the shortcut right away. That wouldn't be me. See, when I was in school and I learned how to divide fractions, there was a rhyme that was kind of going around which was based on an old military rhyme. It said, "Yours is not to reason why, just invert and multiply." In other words, don't question it, don't try to reason it, just do it. But that's not me, okay? So you and me, we're gonna actually reason through this so that we can see why the shortcut works, and then we'll be able to confidently use that shortcut knowing I know what it means, okay? Up across the top, you see this term called multiplicative inverse. That's actually the name of the process that we're going to use as a shortcut. Let's talk about how it works. Now, I picked a nice easy example here. 3/5 divided by 1/5. Considering what you did in the last lesson and on the last exercise, are you pretty confident you know what that means? Basically, I'm starting with this 3/5 of something. In other words, I had a whole that I cut into 5 pieces, and I wanted to know if I just focused on 3 of those, how many fifths would that be? Okay? Now this is pretty easy just to think through. How many fifths do you think fit into 3/5? Well, 3 of them, right? Okay? And another reason I put this up here is because I wanted you to see something that I'm not really going to go into too much, because you won't see it too much, and that's common denominators. Notice this division problem, both of these fractions have a denominator of 5. Anytime you see common denominators in fractions, you can just divide the top, and that'll give you your answer. So, in this example, if I wanted to, I could just say, oh look, the denominators are common, 3 divided by 1 is 3, done. Okay? But I'm not really going to go into that too much. So, let's talk about how I use multiplicative inverse as a shortcut to solve this. First thing I'm going to do is I'm going to write this as what they call a complex fraction. In other words, I'm going to use this division sign to tell me that I can write a fraction with these fractions. Here's 3/5 in the numerator, and here's 1/5 in the denominator. Before we go on, I want you to make sure you're okay with the fact that this and this tell the exact same story. 3/5 divided by 1/5. This one, 3/5 divided by 1/5. Okay, they mean the same thing. Nothing tricky, nothing algebraic really about it, but just know that they mean the same thing. Okay? Now, I'm going to copy that fraction down here because I'm going to do something kind of weird with it. I'm going to get rid of this. What I really want to see happen is I want a nice problem here. I want a fraction here that has lots of information in the numerator and a 1 in the denominator. Now this does take a little bit of algebra here, but kind of try to follow me through. If I multiply 1/5 by its reciprocal, in other words, if I flip this upside down, I get 1, okay? This is what they call an identity. This is a multiplicative identity. Anytime you multiply a number by its reciprocal, it's 1, okay? However, as we've mentioned many times in this course already, anytime you change one part of a fraction or a ratio, you have to do the same thing to the top or the other end of it. So if I multiply 1/5 by 5/1 because I want 1 in the denominator, I have to do the same thing in the numerator. Okay? Now, this is going to give me 1 times 5 over 5 times 1 in the denominator. 3 times 5 is 15 over 5 times 1 is 5 in the numerator. All I did was multiply straight across, okay? And notice that multiplying 1/5 by its reciprocal helped me reach my goal, because 5 over 5 is the same as what whole number? 1, right? So I have 1 here, and here I have 15 divided by 5 is 3. And this is the same as just writing 3. Okay? Is that the answer to this? Indeed, it is. Now, what I just did here, if you're looking at this and your eyes are kind of glassed over and you're like, what is he talking about? Well, basically, I just wanted to show you that if I multiply this fraction by its reciprocal, because I had to get this into 1, right? That it gets me the answer to this division problem. Okay? This is the reasoning behind why I'm going to do the shortcut that I'm about to do. Because watch, if I get rid of this, and I get rid of this, because it's just 1, it doesn't matter, and I get rid of this, and I just look at this, this turned into this, okay? I started off with this part right here, which was just this. And then I said, okay, but I don't want 1/5 in the denominator. I want 1 in the denominator so that I can come up with an answer. And when I multiplied by its reciprocal, I knew that was going to give me 1 because that's an identity. But I had to do the same thing to the top. This is what they call multiplying by the multiplicative inverse, or reciprocal, to find the answer to a division problem. Okay? So here's my reasoning, and hopefully you've already written this in your journal, because I'm going to erase it and show you how to clean all this up now that we've reasoned our way through it and we found out the right answer. How do we make this easy? Well, instead of going through all the steps, I can just write 3/5 times the multiplicative inverse, the reciprocal. Okay? So basically I skipped like 3 steps right there, and I just wrote the numerator of that fraction. And from here it's just multiplication straight across. Okay? 3 times 5 is 15. 5 times 1 is 5. And then 15 divided by 5 is 3. In many schools with many teachers, they'll actually call this KCF. Okay? And since we've gone through the reasoning behind it, I'm more comfortable sharing this with you, where it basically says when you're faced with division of 2 fractions, you keep the first fraction, you change the operation from division to multiplication, and then you flip the second fraction. KCF. Not KFC. I don't like KFC. It's too greasy. KCF is keep, change, flip. Keep the first fraction, change the operation, flip the second fraction. Okay? Let's try the shortcut before you jump into your exercises. And then we're also going to check our answer. Okay, so let's start with a fraction that's a little more complicated. Here's 6/7, and we're going to divide that by Let's go with 8. Let's make it weird, okay? Now looking at this, I'm asking myself, if I have 6/7 of something, I want to know how many 8s are in that 6/7. So if I only have 6/7 of a pie left, because I ate a piece after cutting it into 7 pieces, how many 8s is that? That's even kind of hard to visualize, right? So I could go through all the steps of reasoning through the multiplicative inverse, but since I already did that with an easier example, I'm pretty confident that it works. So I'm going to use the KCF, keep this fraction, change this operation, and then flip this last fraction. Okay? And now it's just multiplication. 6 times 8, 48. 7 times 1, 7. This is not a nice, pretty division problem, but if you remember how to change an improper fraction into a mixed number, you could do that, and it might help you picture exactly what this answer means. So over here to the side, I'm going to put 48 divided by 7. I know 7 goes into 48 6 times, which is 42. Numerator, denominator, right? So if I had 6/7 of something left over, and I wanted to know how many 8s were in that, this tells me that there are 6 8s and 6/7 of an 8. I know that sounds really weird, but that basically means that if I were to try to find out how many 8s are in 6/7, it's almost 7. So there are almost 7 8s in 6/7, okay? Keep, change, flip. Let's try one more, just so we can practice the keep, change, flip thing one more time. Let's say that we have 5/6 of something, and we want to know, let me try to make this end up kind of evenly. We want to know how many 12ths can fit into that. Okay? So we have something cut up into 6 pieces, and we're only focusing on 5 of those, so we don't really care about this one too much. But we want to know how many times a 12th can fit in there. So basically what's happening is every single one of these pieces I'm cutting in half, right? Because a 12th is half as big as a 6th. So I'm basically cutting all of these into a half so that I have 12 pieces. So how many of those are in 5/6? Well, I could draw a model every single time, or I could say, you know what? I already know that if I were to go through all of these steps that Mr. Nielsen went through, I could come up with just KCF. So I'm going to do that to make sure that I don't mess up my counting at all. I'm going to keep the first fraction, change the operation to multiplication, and I'm going to flip this. So it's 12 over 1 instead of 1 over 12. And then I just have to multiply. 5 times 12 is 60. 6 times 1 is 6. 60 divided by 6 gives me a nice even 10. So if I were to count how many 12s I really care about, there's 10 of them. Okay? Practice this on the exercises. On the exercise sheet underneath this video, I have quite a few different practice problems here. And we'll see if you can bring some background information also between fractions, mixed numbers, improper fractions, and stuff like that. I just want to see how that goes, and we'll go over it together when you're finished. So try them, and then meet me on the next video to talk about your exercises.